PhD from MIT, and now he is working at New York University. So maybe I can speculate he defected being from Boston Red Sox fan. Now he might be New York Yankees fan. So
Yankees beat Boston yesterday.
oh, great. Thank you.
That luck with your computer.
Yeah, it's happening. This is annoying. Yeah, well, let's close. Let's show. Let's redo things. Okay. So annoying. Okay, let me close this.
Yes,
The bottom. Okay,
oh,
there you are.
okay, cool. Yeah, so my name is Norman Chow. I'd like to thank the organizers for inviting me and giving me a space to present. And so today I'm here to talk to you about Rossby waves past the breaking point in zonally dominated turbulence. I just want to briefly mention that this is research that's happening in collaboration with the Simons collaboration on wave turbulence. So this is sort of more of like a mathy side of things. Okay. And so first, for some background on the sort of phenomena that I'll be looking at is that typically I'm going to be looking at structure formation in natural and engineered flows. And so on the right-hand side here, I have two pictures. One is a picture of Jupiter taken by Juno, I believe. And you can see kind of, the beautiful banded structure that we're familiar with in Jupiter. And on the right side of this picture, I actually have a picture of a random gyrokinetic simulation. I just picked it from a random recent paper. But one thing that I want to draw your attention to is that even though both of these systems are known to be turbulent, there's actually a lot of structure that we can see in these flows. Again, we have these bands in Jupiter, and on this right-hand side, I've put these green arrows to highlight this sort of banded flow structure that we can see in these gyrokinetic simulations. Okay. And so the point I want to make here is that despite turbulence frequently being thought of as a mixing process, what we see in nature and in laboratory systems is that fluid and plasma turbulence frequently exhibits the spontaneous emergence of structure from mixing. These can oftentimes manifest as long-lived and spatially organized coherent flows, like again, the bands of Jupiter. And so the formation of zonal flows in particular are ubiquitous in magnetized plasma and geophysical turbulence. And these are very visually striking, like in these photos, but they're also key to the regulation of mixing by turbulence. And so, we want to understand these for both climate and fusion energy applications. Two rather related problems, interestingly enough. And so the big picture of what I'm going to try to tackle here is the challenges that self-organization adds to trying to understand these turbulent systems. And so turbulence is typically characterized by huge, like a mind-bogglingly huge number of degrees of freedom active across many scales. And so quantitative theories of turbulence, we usually go to some sort of statistical description, hopefully involving a small number of parameters. And so the famous example being the K41 Kolmogorov spectrum. Here we describe some statistic of interest, like the turbulent energy, in terms of just two parameters, some k naught and some epsilon, which is the flux of energy through scales. And then that describes the, and then k here is just your scale, your wave number k. But one challenge is that when we have these structures in turbulence, the structure and memory of these coherent flows that form resist statistically homogeneous description. And so again, looking at this picture of Jupiter over here, we can see that these bands are correlated with the turbulence in the, or at least by eye, it looks like the turbulence is correlated to the banded structure of Jupiter. And it's correlated in a non-trivial fashion. It's not just like, oh, you subtract out the bands and then you get, you know, some isotropic homogeneous turbulence. It really looks like there's some non-trivial imparting of structure and memory into the turbulence by these large-scale coherent structures. And so big picture, what we want to tackle here is how can we describe the dynamics of flows that exhibit this type of spatiotemporal structure? And so I'll be focusing on zonal spatiotemporal structure here. Okay. Now, as for the setting, why do I have both a tokamak and a gas giant planet? I'll be working in the setting of drift Rossby waves in both magnetized plasmas and planetary atmospheres. And so to point out why we can do this, I just want to point out similarities between the equations that govern these two systems. And so, for example, first line here, we have the magnetic force, it's a V cross B force, and the Coriolis force on the right-hand side. And notice that they have a very similar structure. The next analogy to draw between the two, on the right-hand side, sorry, that's left. On the left-hand side, on the plasma side of things, we have the gradient of the potential, so the electric field, balancing the E cross B drift across the magnetic field. And so that's, you know, the definition of the E cross B drift, which is the dominant drift in a magnetized plasma. Correspondingly, we have the geostrophic balance, which we saw in some of the lectures today, again, having a very similar form to the E cross B drift. And so again, you have this sort of mathematical analogy between the two systems. And so finally, how these kind of combine to give us a similar type of wave between these two systems known as drift Rossby waves. On the left-hand side, in our plasma world, the electrostatic potential will arise in order to enforce quasi-neutrality. So, you know, electrons and ions, they have different dynamics. The electric field based in sort of the most basic picture, the electric field is enforcing this quasi-neutrality constraint because the electrons and ions are doing something different. That electric field then leads to an E cross B drift, leading to, here in this picture, we have some density gradient, and this leads to some, you know, if you perturb this density gradient, this leads to a drifting wave. So that's how you get drift waves in plasmas. Vice versa, on the planetary side of things, you have a rotating planet, and then if you disturb some, you know, fluid line, in order to conserve total angular momentum, because the planet is spinning, this fluid will pick up a local vorticity in order to, and that will again create this sort of drifting wave, creating a Rossby wave. So that's the sort of bridge that between these two systems. Okay. And so with that setting in mind, that brings us to what the talk overview will be about. And what I'm going to propose as a sort of answer to this question of how do we describe turbulence and spatiotemporal coherence, I'm going to propose a picture for the dynamics of large-scale coherent flows in quasi-geostrophic turbulence, which I haven't introduced yet. But and that picture can be summarized very briefly as nearly integral Rossby waves past the breaking point in zonally dominated turbulence. Okay, and so we've talked about zonal flows, and so kind of an outline of the rest of the talk, I'll talk about what do I mean by Rossby waves, you know, strictly speak like being precise about that. Next, I'll talk about what is meant by nearly integrable, where does that come into play? And then finally, I'll explain past the breaking point and kind of an outlook into what this means for other systems. Okay, cool. And so to start off explaining what I mean by Rossby waves, we're going to be considering the stochastically forced barotropic beta plane quasi-geostrophic, that's QG, equations for the potential vorticity. Okay, and so we saw a lecture on the potential vorticity. The equations, if you're interested, are written down here. I'll mention that these are a prototypical two-dimensional model for the gas giant atmospheres, Jovian atmospheres. And the way that it connects to plasmas is that it can be considered a special case of the Charney-Hasegawa-Mima equations, although there's some bumps there that I'll talk about in a bit. If you're not familiar with these equations, I'll just briefly mention what's contained in them. Kind of there's four main parts. There's an advection part, that's the part in blue. Essentially, it's kind of like, it looks almost like an Euler equation. There's some advection by a stream function psi, and then there's also a background gradient of potential vorticity beta. So there's an advection term. In this model, I'll be considering dissipation by both friction and I'll be using hyperviscosity. I'll talk about that in a little bit. Here, I'm going to be looking at forced, stochastically forced systems. And in particular, I'm going to be taking a small scale forcing, I'll describe that in a second, and white in time forcing. All right, and finally, the final bit that we consider here is the relationship between the potential vorticity Q and the stream function psi, which determines the flow. And this is given by something that I'll call a quote unquote Poisson equation, because it allows you to solve for the electric field in the plasma context. One thing that I'll point out is that one difference between these QG equations and the Hasegawa-Mima equations that plasma people might be familiar with is that there's no gyro radius here. So this is not a legitimate limit of the Hasegawa-Mima equations. So just keep that in mind. Okay, cool. So with these equations in hand, what I start out with is by looking at these equations using direct numerical simulations. Okay, so here are some gory details about how I do these simulations, but the key points are that this is a fairly reasonable resolution, 2048 by 2048. I'm using a W periodic box. Here's some parameter values. And then another thing to mention, because hyperviscosity got brought up, I'm using a lambda, or not lambda, delta to the fourth hyperviscosity. The other thing is that the forcing will be isotropic, or and annular in K. And so there's some ring in K space, and then I force a range of wave numbers between 14 and 15, which in this case would be K is also the wave number. So it's relatively small scale compared to the box size. Okay. I'll be considering two cases with different forcing amplitudes. And then roughly speaking, the forcing amplitudes are chosen such that the average kinetic energy will be equal to about 1 in case 1. And then this is about 0.1, I believe, in case, or 0.05 in case 2. Okay. Here on the right-hand side, I've just picked a color screenshot of one of these simulations from here. And so we can see that this looks fairly like this. So what's plotted here is a total potential vorticity. So that value Q plus beta Y. And so the color scale is showing this total potential vorticity. And we can see that this looks like fairly well-developed turbulence. There's lots of little eddies and waves and things going on. Okay, cool. So, yes, question.
I don't think that's, if there's total potential vorticity, you can see it when you gradient.
Yes, that's because I am using a, so this is a, it's a cyclic color scale.
Oh.
Yeah, cool. All right, so, what do I mean by Rossby waves? So first thing I'm going to do is try to numerically identify these Rossby waves. Okay, and the way that I do that is through the proper orthogonal decomposition. I guess Steve talked about it briefly, but we don't need to worry about the details. But essentially what the proper orthogonal decomposition is going to give us is a number of orthogonal modes, which are going to be ranked by their contribution to the time average energy of our DNS snapshots that we're going to use. So I take, some number of snapshots, in this case, 256, they're going to be equally spaced in time. I perform this POD on it, called a black box, and we're going to get some modes which carry some fraction of the energy content in those snapshots. Okay, cool. And so I have an example of some of these modes here on the right. These are indexed by 0, apologies for that. But so for example, the highest rank POD mode, these are extracted from case 1. Again, we take the snapshots, we run this analysis. In case 1, for example, the highest rank mode is this zonally symmetric mode. And so this is in fact the, and what's plotted here is the stream function psi. And so mode 0 here corresponds to a more or less steady zonal flow. And so this is a stream function of the mode on the top, and we can see the amplitude corresponding to the POD mode on the bottom. And so this is relatively steady. And so this is saying that the mode which contributes the most energy to the flows is, as expected, a zonally symmetric zonal flow. Okay. The next few modes looking at, for example, mode 1, so the mode contributing the second most energy, this mode shows both a lot of coherence, both spatially, it has this very well-defined spatial structure, as well as temporally. Okay, and so I guess I can't zoom in here, but if you look at the, if one were to zoom into the amplitude trace here, what you would see is actually a very steady sinusoidal oscillation in the amplitude of this POD mode. Okay, there's a little bit of aliasing effects there, which is a little bit of noise. But finally, if we go to even higher and higher modes, so for example, this is mode 37, what we find is as we go to higher and higher modes, both the spatial and the temporal coherence gets steadily worse and worse. And so here we can see no discernible spatial structure and no discernible temporal structure. Okay. And so again, because these modes are orthogonal, we can, and ranked by their energy contribution, we can ask what is the contribution of each mode to the total energy of our snapshots. Okay. And what we find is that about 72, for our case 1, so with larger forcing, we find that about 72% of the energy is stored in the zonal flows. But one thing, and this is rather surprising, and I really want to emphasize this, if we look at the energy in the next 4 POD modes, and so these POD modes, it turns out that they're paired in like sine and cosine pairs. So this is essentially, it's 4 POD modes, but 2 actual modes. 24% of the energy is in just those 2 modes. We can or put it another way, about 86% of the non-zonal flow energy is in just those 2 modes. 1% of the modes carry 99% of the energy, well, something like that. We see something very similar for case 2. I haven't shown the example modes here, but again, we find that most of the energy is in the zonal flows. But again, a very small fraction of the POD modes carry almost all of the non-zonal flow energy. Okay. And so why do I call these POD modes Rossby waves? Is that we can compare these POD modes to eigenmodes, to Rossby waves that we can just compute. And so I'll mention that in the absence of forcing and dissipation, pure zonal flow states, U of y, solve exactly the QG equations. And so we can compute eigenmodes. Eigenmodes of the system linearized around these exact solutions, linearized around these exact zonal flow solutions. And so here I take the time averaged zonal flow profile from the simulations. I just numerically compute eigenmodes, and I write down the equations and solve them. And we can compute eigenmodes and eigenfrequencies of the Rossby waves. Okay. We can also compare against a sort of flow-free dispersion relation. And so this dispersion relation might be something that you've seen more frequently, is that if you have a zero flow state, what do the Rossby waves look like? Okay, and so we can compare both the spatial and the temporal structure of the eigenmodes with the POD modes here on the right. Okay, and so here, again, I mentioned these POD modes are paired. So for example, in case 1, modes 1 and 2 are paired. They essentially form these sine and cosine pairs. Okay, we can compare that against a corresponding eigenmode. So again, we just solve linear, just solve a linear eigenmode problem, and then numerically, and then we just look at the eigenmodes, look at which one looks the closest to that. And we can see that the eigenmodes and the POD modes look really similar to each other. Furthermore, what is found is that the eigenmode frequencies, so the eigenfrequencies, really well match the frequency of the oscillations of our POD modes. Okay, and so here are just some numbers. One thing that I want to point out is that the match is a lot better than the match that you get purely by using the dispersion relation. And so this is kind of an argument that it's really the eigenmodes that are important, not just the the Fourier modes that you would plug in to the dispersion relation. One final thing that I'll remark is that the eigenmodes are actually really capable of capturing really fine spatial detail that we see in the POD modes. So for example, in these POD modes on the bottom, you see this sort of spatial feature on this band over here. This spatial feature actually is reflected in the eigenmode over here. And so one thing that I want to point out is that the spatial localization, corresponds to a broad, like a broadness in wave number. And so this is not, again, these are not just, waves at a single Fourier mode. They correspond to waves that have, structure across space and therefore structure across K. All right. And so those are our Rossby waves that we're going to talk about. And so we have to ask, okay, how can we describe these Rossby waves? Okay. And so a first approach might be to say, okay, these are really coherent waves. Why don't we just use weak, quote unquote, weak turbulence theory? Some things that I want to point out is that these waves are very ambiguously nonlinear. They reach really large energies, significant energies, both in absolute terms, but also relative to zonal flows. Here's another example of how they're ambiguously nonlinear. We can compare the maximum flow velocity induced by the wave, and we can compare that to the phase velocity of the wave. And so this is a common estimate of, say, the linear to the nonlinear timescales for these Rossby waves. And what we find is that, for example, in case 2, this ratio is about a third, And so one question is, why are these Rossby waves surviving so long despite their rather large amplitudes? You would expect something like this, if the linear to nonlinear timescales is a third, you'd expect the wave to oscillate 3 times or 10 at most and then just disappear. But what we find is that these waves can oscillate like, many cycles, and they show no sign of going away. And so first question, why are these Rossby waves surviving so long? The second point that I've already mentioned is that we have this broken statistical invariance in K-space. These are really not, just Fourier modes. They really are the eigenmodes. The eigenmodes, and again, these eigenmodes have this structure which, if you convert from real space to Fourier space, they have a structure across K space. And so why do these modes maintain this spatial structure? That's another question that we want to answer. And so in the following, we're going to be focusing on what I'm going to call coherent large-scale Rossby waves. And so the coherence is quantified by some statistic. I didn't just look at it and pick which ones. There's actually something behind that, but I won't go into the details. One thing that I will mention is that we can see kind of the amplitude contributions of these large-scale coherent Rossby waves here in case 1 and in case 2. And so in case 1, there's about 5 waves that satisfy this coherence statistic. And importantly, like the largest amplitude wave does in fact have that, is in fact coherent. And similarly in case 2, the largest amplitude waves are more or less the coherent ones. And then again, in case 2, there's more like 20 waves, which satisfy this coherence criterion. Okay. And so here we're going to start talking about near integrability, trying to see, how that connects to answering those 2 questions that I posed earlier. Okay. And so in order to do that, first, we're going to connect the QG equations to finite dimensional Hamiltonian mechanics. Okay. And so I want to point out that in the absence of forcing and dissipation with, Galilean shift, you can write down the ideal QG equations in this rather simple form. In particular, this first equation here, the advection equation, this looks like a Hamiltonian evolution equation with a time-dependent Hamiltonian psi plus Cy, where C is some Galilean shift that we can introduce. Okay. Now, we know that there's this common trick that if you have a time-dependent Hamiltonian, you can turn it into a time-autonomous system by introducing a new momentum coordinate conjugate to time and redefining your Poisson bracket. Okay, that allows you to convert this advection equation from this time-dependent equation into a single involution or commutation condition, where we have, instead of dq dt is equal to Poisson bracket something, we have Poisson bracket of 2 new fields called psi hat and q hat. The commutator of the, or Poisson bracket of these 2 guys will be equal to 0. And that is exactly equivalent to the evolution equation after we use this little trick. Okay, now we notice that we have 4 phase space variables, x, y, t, and c, and we have 2 variables or 2 fields which are in involution. Okay. And so in particular, psi hat and q hat are independent integrals of motion for dynamics generated by this Hamiltonian minus psi hat. This Hamiltonian corresponds to flow along Lagrangian fluid trajectories. Okay. And in particular, if you write down, if you have some evolution parameter S, you'll get dx, ds, or things like that. This Hamiltonian minus psi hat generates exactly flow along, Vx, Vy, and then your T just evolves like your evolution parameter S. And so this psi hat is, generating Lagrangian fluid trajectories. Okay, and so we get this really nice and cute theorem is that if we have some suitably regular time periodic solution, Q, to the ideal QG equations, Lagrangian flow specified by this Hamiltonian, or well, I mean, it's just the Lagrangian flow. So the Lagrangian flow, which is specified by that in this extended 4-dimensional phase space, is integrable in the Louisville sense. Okay, I'll remark that the time periodicity is actually crucial to here, but I won't go into details. All right. Now, how does this connect to eigenfunctions? Okay, I'll remark that again, basic zonal flow states have our solutions, time periodic solutions to the QG equations. And so therefore they have integrable Lagrangian flows. Well, that's no surprise. All right. But what we can say now is that let's look at, say, a perturbation, epsilon Q1, which we don't necessarily assume to solve the equations of motion yet. So we just take an arbitrary perturbation and we ask, okay, we perturb the flow by this PV perturbation. What is going to happen to this involution condition? Okay, so we just put in the epsilon and then we do out the math. We get that the Poisson bracket of our perturbed psi with our perturbed Q is going to equal some term which has a epsilon to the 1 dependence, epsilon to the squared dependence. Now, if we set this remainder, these are going to be two remainder terms on the right-hand side, which are barriers to integrability. If they were 0, then we would still be integrable, but they're non-zero, so we're not quite integrable. If we set the epsilon to the first power remainder term equal to 0, if we collect all the terms, set the epsilon to the power 1 term equal to 0, what we find is that this condition R1 is equal to 0 turns out to be exactly equivalent to the QG equations linearized around our basic zonal flow state U of y. Okay, so in other words, this eigenfunction equation that we solved just a few slides earlier also is exactly this near integrability condition where we remove the epsilon to the first remainder term. And so kind of the key conclusion there is that regular eigenfunctions give both approximate solutions to the equations of motion, because they're eigenmodes, as well as nearly integrable perturbations to the zonal flow Lagrangian dynamics. Okay, and so what exactly does that mean? And so I'm going to draw a connection here now between integrability and laminar to turbulent transitions. Okay, so if you're not familiar, integrability, I'll just briefly mention one of the consequences of integrability is that we can have action angle coordinates to describe our trajectories in our Hamiltonian flow. And in particular, one thing that we get is this so-called foliation by invariant tori. A sort of a canonical example of that is this pendulum Hamiltonian. I've plotted the trajectories of a pendulum in phase space under this Hamiltonian. And you see that the trajectories form these nice closed curves. These are the invariant tori. And one thing that I want to mention is this word foliation is this process of splitting into thin sheets or laminae, AKA a Hamiltonian flow which is integrable is also a flow which is laminar. Okay. And now how does this connect to near integrability is that the Kam theorem tells us that in some sense, many invariant tori of integrable systems persist under small perturbation. One thing that I'll remark is that on these surviving invariant tori, we have not just an averaging of perturbations by whatever we're perturbing it by, but in fact a total cancellation for all time of our perturbations. So absolutely no diffusion. Okay. And finally, I'll remark, and so what this tells us is that we have this laminar flow, which by the Kam theorem tells us will somehow survive perturbation. And then finally, I'll remark that the chaotic regions in this picture will then correspond to non-laminar or turbulent flow. Okay, cool. So having established what I mean by near integrability, we can finally talk about what do I mean by the breaking point and past the breaking point of Rossby waves. Okay, So what we can do is we can numerically now look at what are the actual dynamics of the Lagrangian flow, which is induced by our large scale coherent waves. Okay. And so what I do is I'm going to take our large scale coherent waves, I'm going to superimpose them all together. And then I'm going to take their flow. This is going to be some flow stream function psi corresponding to these waves. I'm going to approximate this flow as periodic. In general, these eigenfrequencies are going to be incommensurate. And so you have some quasi-periodic flow, but you just take a big enough period and then you can approximate you can approximate this stream function as being periodic. I'll remark that this corresponds to taking a remainder term R1, not strictly equal to 0, but just small. Okay, so that's what that means. Okay, and so we can take, now that we have this periodic flow, we can then analyze this periodic flow using Poincare sections. Okay, and so Poincare section, if you are unfamiliar, what you do is you take a point, you follow it under one period of your flow, and then you mark it down, and then again, repeat, mark it down. Sometimes they're also known as stroboscopic sections. And so essentially you initialize these things with a bunch of particles, and they follow along the flow, and you eventually see the trajectory that these particles map out under the flow. Okay. And so using, again, those large scale coherent Rossby waves I mentioned earlier, we can construct these Poincare sections. And what we get is something that looks like this in case 1, something that looks like this in case 2. I'll remark that the coloration here, this is a correlation dimension, which I computed for the trajectories in the Poincare section. And so these purple ones correspond to trajectories which are approximately one-dimensional. And so these are the invariant tori. And then the trajectories, which are green or yellow, fill space. They have a correlation dimension of 2. And so space filling trajectories are the chaotic ones. Okay. And so we can see that in general, the majority of tori, or the majority of the Poincare sections are taken up by these tori, these surviving invariant tori, the CAM tori. Okay. And the chaotic regions are actually rather confined. Okay, these chaotic regions in green and blue are rather confined. Okay, cool. And so kind of what does, kind of analyzing what does this mean? How does this connect? And, is this relevant at all to our turbulent state? Okay, the first thing that we can see is that this sort of statement that chaos will imply mixing in large scale wave flows. Okay. If we focus first on case 1, we can sort of take this chaotic region, which I've highlighted in orange here, and we can compare how the location of this chaotic region correlates to the location of the mixing of our potential vorticity gradient, across the entire plasma, or sorry, not plasma, but QG simulation. Okay. And so what we find is that in every region where there is chaos, which is these orange regions, what we find is that the PV gradient is pushed below the background value of beta. Okay, and so that's what I mean by chaos implies mixing. We can see that this holds for case 2 as well. Wherever there is a chaotic region, this correlates extremely well spatially with where the mixing is happening. One thing that I'll remark is that it doesn't go the other way around. There are some mixing regions which are not captured by the chaotic regions. And we can talk about that in questions. But another thing that I'll point out, for example, is that these mixing regions are not just in the middle of like our jets. For example, this mixing region is displaced from the center of the jet. And in fact, it exactly matches the displacement of the chaotic region from the center of the jet, towards somewhere else. Okay. And so, yeah, we have a very strong correlation between chaos in these Poincare sections and mixing the actual DNS. Now we can go even a little bit further and ask, beyond the zonally average sense, how is this chaos showing up in our DNS? And so I'm going to make this claim that invariant tori bound what I'm going to call Rossby wave surf zones for our large scale wave flows. Here we're going to, again, focus first on case 1. Again, we have the bounding tori of our chaotic regions in orange here. We can look at a DNS snapshot And we can overplot our surviving invariant tori, which bound the chaotic regions here on the right. And this DNS snapshot, so again, what I'm plotting here is the total PV, Q plus beta Y. But here, this is going to be colored by the length of the PV contour at that value of the PV. And so essentially what this is measuring is, the PV contours, they start out undisturbed, but as they get disturbed, they get all mixed up and their length is going to increase. And so these bright yellow regions correspond to regions where we have more disturbance of the PV contours, AKA longer PV contours. And so what we find is that not only do these chaotic regions match in a zonally average sense, the mixing, we find that these invariant tori are also able to capture beyond the zonally average sense, the mixing that we are seeing in these snapshots. In particular, we can see here this region of bright yellow, well, brighter yellow. It has this slight bulge, which reflects the shape, which is reflected in the shape of the bounding invariant tori on the left. We can also look at case 2. Yes, sorry, I am almost done. Okay, we can also look at case 2, and we can see, again, take bounding tori for our chaotic regions. And again, we see these bounding tori match up very well with these regions of bright yellow, which correspond to mixing of the PV, okay, for both of these regions. Okay, cool. And so kind of now to take that together and then talk about the physics. What does this mean? Like, why does this matter? Okay, all right. So starting off with this observation that chaos implies mixing. Basically, what we're finding is that wave breaking in this chaos is leading to wave breaking in these so-called surf zones, which is something that's been well described. Many works on that. But here I'll remark that, and so we know it's well known in the literature that this sort of wave breaking in the surf zones helps maintain this PV what's known as the PV staircase. Okay. Here in this picture, this PV staircase is going to act as a wave guide for Rossby waves. Okay. Now these Rossby waves we saw are in some sense nearly integrable. Okay. And this leads to several consequences, which we can chain together. All right. The first consequence is that, again, we saw from the Poincare sections that most of the invariant tori survive. Okay. And so in some sense, not all non-zonal energy is turbulent energy. In fact, what we find is that because we see most of the invariant tori survive, in some sense, the flow is dominated by a temporally and zonally varying laminar flow. Okay. And so this near integrability gives us a way to actually describe this laminar flows beyond a temporally stationary or zonally symmetric sense. Okay. The next consequence is that there's going to be a near alignment of the PV contours with our surviving invariant tori. And in particular, this is going to give us a long time stability of our PV under the Poincare map. And so what I mean by that is that on this right-hand side, what I've plotted here are basically contours of the perturbed PV, of the wave perturbed PV. So we take the waves, we look at their PV contours, and we can evolve those PV contours themselves under the Poincare map, and we can ask what happens to them. And so in this bottom contour here, this contour is localized to one of the laminar regions of the flow. And this essentially stays constant. This PV contour stays constant under any number of any number of iterations of the Poincare map. And so in this sense, this leads to a long time stability of the waves because this leads to long time stability of waves which are localized to laminar regions. And then one final comment is that non-modal PV perturbations. So this question of like, why do we have waves and then nothing else? One thing that I'll remark is that anything else, anything that's not waves, produces perturbations which are not aligned with this very large energy laminar flow. And so those perturbations would get sheared apart, similar to an OR mechanism. Non-modal perturbations get sheared apart. And so that's a conjecture as to why we only see waves and nothing else at these large scales and large energies. Okay, cool. And so essentially, if we summarize this, this gives us in some sense, a self-organization principle that can explain why do our Rossby waves live so long? Why are they oscillating so long at such high an amplitude? And moreover, why do they organize specifically into the Rossby waves and not into any other large-scale structure? Okay, cool. All right, and so for Outlook, this is kind of just future work. I'll skip this slide. I'll briefly mention that many other flows have sorts of, at least formally, have equations that look like the QG equations. So for example, the Hasegawa-Wakatani equations, there's this advection term that's over there, reduced MHD, planar reduced MHD rather. Also, we have a very similar form for this advection term. And so one outlook is maybe we can look at near integrability playing a role in other flows. Also remark extension to non-2D flows. I will skip this, but the main point of this slide is that there is actually integrability results that exist in non-2-dimensional flows. For example, in 3-dimensional Euler flows, vortex tubes, which are force-free but non-Beltrami, actually are also integrable in a sense. And so this is not just something specific to 2D or to 4D or things like that. Okay. Cool. And so I'll end with the talk summary is that we have the QG equations, which bridge fluid and plasma systems. We have this proposed picture for the large scale coherent flows in the QG turbulence. And we explored how near integrability can help explain why these Rossby waves that we see kind of close the loop. It explains why they survive so long. All right, cool. Thank you for your time.
Any question? Simultaneous. So
Maybe just the big question here is the origin of zonal flows in the first place, which you don't directly address. You do assimilation, you take in various forms of friction and damping or forcing. Of course, there's a zoo of those things that you can do and you get all different things. So once you have established a zonal flow, you can look at your eigenvalues, you can then look at the maintenance of the zonal flows. That's what your main emphasis here is. That once you see a zonal flow like some pattern on Jupiter or something, why is it staying there for all the time? Is that the main purpose of this?
Yes. Yeah. So to put a little bit in context, this is sort of dealing with like an intermediate time scale. So there's been recent work showing that zonal flows like evolve on an extremely long time scale. There's like the work by Simonet and Boucher on like the large deviation theory regarding the evolution of the zonal flows. And so one motivation of this work, which I didn't mention, is that there's this assumption somehow that there's this fast turbulent time scale and then this very slow zonal flow evolution time scale. But one thing that I want to point out is that there's a lot of non-trivial intermediate timescale stuff that goes on. And then, yeah, so this was trying to characterize that intermediate timescale.
Yes, since you were referring to the Kolmogorov Arnold theorem, I was surprised you didn't use, or probably not, the Cherenkov overlap parameter to characterize the topology.
Yeah. So one complication here that I'll mention is that one difference between this system and the like the traditional Vlasov system is that actually we have a large diffusion of regular eigenmodes, so modes which are not completely non-resonant. This can't happen in the Vlasov system. And so, for example, these red bars actually denote where we have the resonant modes, and then the green ones are the non-resonant. No resonance with the integrable tori. And so it ends up being complicated because there's no first order resonances that are important here. And so you have that. And then these are also very large amplitudes. So you don't know a priori if it's like the second order or the third order or nth order resonance that's going to be important. So that's why I didn't use that island overlap criterion.
So how near is near? And is there a relation between proximity and the amplitude of the Rossby wave that you can hold?
So When I gave this talk at UCSD, I thought there was. Then I looked more, and then it doesn't appear. The story is not so simple. So first, as to how near is near, one thing that I want to point out historically, actually, so there's been this look at, there's been studies of like the standard non-twist map, which is relevant to these sorts of zonal flow with the non-monotonic zonal flow profiles. One interesting thing here is that what I'm finding here is that these modes are like strongly non-resonant, whereas a lot of the literature, so standard map, first order resonance is not going to be applicable here. The standard non-twist map, it turns out that for reasons, they put the Rossby wave like exactly resonant like here. So that actually also turns out is not what I'm observing here. Like, so, it's like standard map, it's like, here's your resonances, you live here. It's not standard non-twist, you live right here. This, we live out here, which, so yeah, I couldn't find much discussion on what the, how you actually get into chaos in here. And then, yeah, so the question of how that affects the amplitude of the waves. Maybe I will mention one interesting thing is that, so it turns out that these waves kind of, the most energetic waves actually look a little bit like frontal waves, actually. And so as these PV staircases steepen, it's like the Rossby waves that get forced out of the regions where there's no more PV gradient. So it turns out that like, and so this is one of the reasons that this is a QG talk and not a plasma talk, is that it's possible for Rossby waves to live on the staircases, but then affect flow in the flat part, the steps. Okay, and so that's illustrated here. We have these, these are sharp jets. So these Rossby waves are more or less like the mixing that this wave causes is like over here. And so the story of how the mixing influence, like how the chaos influences the amplitude of the wave is a bit more complicated than just as soon as you get mixing, the wave starts to lose energy.
Can you test whether the PV mixing could be calculated, given the chaos, could be calculated by a Fokker-Planck equation?
I guess, I'm not sure.
Something fancier, right? You would type, in principle, for things like the, for when you have stochasticity, it's the Fokker-Planck or quasi-linear calculation isn't bad. Think of magnetic field lines, for example.
Yeah. So I think one thing is that it's like, so like the scale of these mixing regions, for example, looking here, the scale of these mixing regions is like comparable to the scale of like the filaments or the structures that like get drawn out in these mixing regions in some sense. So I'm not, a priori, I'm not sure if like you could have a Fokker-Planck equation properly describe the PV, speaking of blobs and, mixing and spreading and things like that. But so, I mean, I haven't looked as to whether or not you can do it or not, but.
David?
You had a slide that kind of related problems or something. One of them was
This one or the other one?
so you got planar reduced MHP, so you mean field in 2D and the field is in the plane.
Oh, no, sorry. This is a field is out of the plane, but then you restrict to, I mean, this is completely artificial system, but field is out of the plane and then you restrict to, this is a parallel basically. Yeah, you're evolving a parallel with that equation.
Where it's in the plane.
In the plane, correct.
And the field is
I guess, I mean, the field, I guess, yeah. So you have a strong magnetic field out of the plane, and then yeah, all the motion is in the plane, and then yeah, you would get, yeah, you don't get any like, I don't remember off the top of my head which terms stay or which terms go, but.
It didn't look obvious to me that was going to look like your system you talked about today.
Yeah, I guess the thing, I mean, I just, the thing I wanted to point out here is that if you have this planar flow, then one of your equations of planar reduced MHD, again, artificial system, but I mean, one of the equations is essentially this time-dependent Hamiltonian evolution equation. And so you can do the same trick where you take psi, you add another variable. So now you have x, y, t, and c. And then this second equation, you can also turn into a single involution condition or commutation, Poisson bracket condition.
Not sure what the analog of Rossby waves is.
Yeah, that's another thing. You want to get an analog of Rossby waves here. So yeah, there's no
How generic or do you think that what you just described is? Because if you jump at your pretty well, you have some not that complex. Another one. For instance, here, if you look at the connection length, the zone, the nodes, they also have very long connection lengths, and still, you know, that's not where you apply. Well, you would miss that part, which, you know, from a flow perspective, is very similar to the one on top. So, if you were not to know the results, just computing that, you wouldn't know which one to plug into. So, how good a diagnostic is it? So, how much of it you learn?
Yeah, so that's actually a very good and important question. So one thing that I want to point out is that one reason why I use the coherent waves only is so we have this Poincare section visualization. Because I mean, we saw that, you know, getting things out of dynamical systems is hard enough. And so it turns out that actually there are activity that straddles the boundary between wave activity and like hydrodynamic, you know, past the Rhine scale sort of activity in this region where we don't capture the mixing. And so it turns out that actually there are another type of localized Rossby waves, which correspond to actually the trapped Rossby wave modes. It turns out that these guys here that I actually do capture are like passing Rossby waves. They pass all the way radially, and it's doubly periodic, so they just wrap around. There's another class of Rossby waves, trapped Rossby waves, which live in, for example, this jet here. Those trapped Rossby waves, they turn out to be they're not regular eigenfunctions. Those are resonant, but then their resonance lives outside of the jet. And then, so moral of the story is I do see those modes, and they can actually go to significant amplitude, but the Poincare section analysis is not able to account for it because they're coherent for maybe 2 or 3 cycles, like maybe 10 at the most, and then they go away. So there are dynamical systems, things that you can do for these sorts of, you know, quasi-periodic, aperiodic, or, you know, localized in time disturbances. But I am reading those papers now, and it will take me some time to answer whether or not those methods that have been developed, and these are very recently developed methods for like, you know, because you know, generalization of lobes to quasi-periodic systems, you know, it's like papers very recent. Moral of the story is I don't know yet. Maybe there's hope, but and there is literature talking about how one might deal with these other waves which are not captured, which you could not capture here.
Are you driving to the conclusion that even in this very simple system, you have 2 means by which you drive the staircase steps?
At least 2.
Yeah. Two very different mechanisms by which you. Is that one of the reasonable conclusions?
Probably, yes. So like, for example, it might turn out that this jet, it might turn out that maybe if you do include these, so essentially it's like these wave packets. You see like, you know, like intermittent sort of Rossby waves that live in this jet. It might turn out that maybe it's some generalization of this sort of time autonomous chaos. It might turn out that it's some generalization, and so maybe you wouldn't call it 2, but at least 1.5 different mechanisms at the very least. And then this is speaking nothing of the small scale junk that happens. So at least 1.5, probably more. Yeah, and actually, in fact, well, okay, there's another thing that you can actually see is that there's a little bit of wave breaking that happens like on these laminar jets in the first place. So at least 2, probably a lot more, maybe.
Just a follow-up to that. I mean, could you, you basically based your analysis on 2 simulations that in different regimes where you form this complicated structure, then you look at the zonal flow, and you get the eigenloads, etc. And you're interested in the staircase maintenance, etc., and the waves there. But could you do something a little more theoretical and actually start with an exact staircase, find the eigenloads from that, and then follow your analysis through? Would you learn something more deeper than what you? I mean, could you basically give a more theoretical description based on a perfect staircase?
That's a good question. I mean, so again, like I alluded to this with like Boucher, Simonet papers on the large deviation theory. So their claim is that like the staircases are always metastable. In the presence of stochastic forcing, staircases are always metastable, and you're going to transition over like exponentially long time scales between the different staircase states. And then they claim that you have this like, you can, by comparing the metastability of the different number of staircase steps, that would allow you to figure out what the staircase step size, like the staircase scale would be, which is the question that people care about. And so in that sense, it's important to describe not just an equilibrium, what's happening with the waves at those equilibriums, but rather also the transition paths. You have like 2 staircase steps, 3 staircase steps. You need to, their claim basically is that it's the dynamics like here, like far from equilibrium, that are in some sense controlling these transition rates between these staircases. And so in that sense, so one thing that I didn't actually mention is that these simulations, they're not run like that long. They're only run for a few frictional relaxation times. And so these arguably are not really in like asymptotic equilibrium either. And so I think the need would be to describe, this like far away from perfect staircase behavior. That's their claim anyways. Well, okay, I shouldn't say that's their claim, but that's how I'd interpret their work.
You are raising hand or no? No. Last one.
To know whether you try to vary the amplitude of your eigenmodes, it's usually or to further simulation to like look for the condition of the breaking point, or maybe the transition to a lower.
Yeah, so I did like vary the eigenmode amplitudes and things like that. It turns out that these eigenmodes, it turns out that the transition to chaos existing like at all is actually quite far down. Like you have to take the eigenmode amplitudes and you reduce them by like about like 1/2 or like 30%, 40% in order to completely get rid of all the chaos. But the thing is that the region of chaos grows rather slowly. I don't know the exact scaling again, because you can't just use the Chirkov island overlap criterion directly. And then I haven't even begun analysis of like, what order resonances are these and things like that. So short answer is it's you bring the amplitude down like 30-40%, you can get rid of all the chaos. But even if you increase the amplitude by a lot, especially the laminar jets, like the staircase steep regions, it's very hard to get the chaos to impinge on those.
Okay, it's time for lunch. So bon appetit.